was sample proportions, which is all the little p hats. Now we're doing sample means, which is all the x bars. So sample proportions are typically categorical when you're doing the p's and the p hats, because an example of a sample proportion is what? Proportion of youths, adults watch The Bachelor. Okay. But a sample mean is something that is quantitative, where you can actually take the mean, right, of a bunch of different numbers. So like household income, blood pressure, those are numbers. So that's a sample mean. Yep. We do those, though. Yeah, we do that. But yeah, it's still it's still categorical. But yeah. All right, we are gonna do this activity today. I know. I tried to make this work. I got a few bags. All right. Uh, your teacher will assemble a large population of pennies of various ages. In this activity, your class will investigate the sampling distribution of the mean year, X bar, in a sample of pennies for simple random samples of several different sizes. And then you will compare these distributions of the mean year with the population distribution. All right, your teacher will provide a dot plot of the population distribution. Oh, I didn't do that. Dang it. And have each member take a simple random sample of 5 pennies. So I'm going to pass the bags around. Take 5 pennies. Write down the 5 years of the pennies. And then put the coins back in the bag. And then find the mean of those 5 pennies. I mostly wanted you to see what exactly we're doing with quantitative data. Yeah, CC. 100. Oh, it's okay. We're going to be okay. All right. Making money. I'll first look at the sampling distribution of X bar. By the way, the true sampling distribution is when you take every single possible sample, right? So a ton of samples, fill them all in, and that would be a true sampling distribution, which would then match the true mean of the population, okay? So a histogram, here we have a histogram of the earnings of the population of 61,742 households that had earned income greater than 0. That's good. That's positive. So over here, you guys, we've got the population. And over here, we've got samples. So this is samples of size 100. So notice this one, we've got people spread all the way over here, some super like wealthy people over here making good money. And for B, so the A is the distribution of earned income in the population of all those people, and B is the distribution of the mean earnings. They took 500 random samples of size 100 from the population. So as we expect, the distribution of earned incomes is strongly skewed to the right because of those really wealthy people, and very spread out. The right tail of the distribution is even longer than the histogram shows because there are too few high incomes for their bars to be visible on the scale. You can't even see them. We cut off the earnings at 400,000 to save space because there's people that make more than that. The mean earnings for these 61,000 households was mu. Okay, mu meaning the true mean, right? That's the true mean of the population right there. Okay, then we've got a simple random sample of 100. The mean earnings of that sample was 66,807. That's less than the mean of the population. But if you take another simple random sample, the mean of that sample was this. That's higher, right? So we can have all kinds of different numbers, but we should still get, if we take many, many, many of them, right, the exact same mean. So both distributions will have the same center as long as we take enough samples and prove similar things true like we did with the proportions, okay? So here's the formulas that you need to know for the sampling distribution of X bar. So again, this is when we draw out of the hat and average them, just like you did with the pennies. Mean and standard deviation. So suppose that This is the mean of a simple random sample of size n drawn from a large population with mean mu and standard deviation sigma. The mean of the sampling distribution is this. Write that down. So this is mu of x bar. Sorry, that doesn't look very good. This is a little x bar. Is equal to the true mean. Okay, just like with proportions, when we did the mean of the proportions is equal to the true proportion. Whoops. Okay, then we've got the standard deviation. This is a different formula. Wow. All right, so a different formula than the P formula when we're doing proportions. So this is when you're doing sampling distributions of X bar. So no decimal, no fraction. You're getting like the year of the pennies or whatever. Okay, so this is sigma of X bar. So this is from the sampling distribution is equal to the true standard deviation. So this is the standard deviation from the population right here, right? Standard deviation that's given from the population. And n is your sample size, right? So in our penny problem, the one we just did, our sample size was 5. We drew 5 out of the bag, right? And if we drew 25 out of the bag, we would be decreasing the standard deviation. Now pay attention to when you're finding the standard deviation of the population or the standard deviation of the sampling distribution. Because there are times where we actually use just the population to do our calculations. You'll see the difference in the problem, okay? And again, what do we have to prove is true when we do standard deviation? 10% condition. Same as the standard deviation before. Now, all these formulas are on the sheet that will be given to you on the AP exam. So your yellow sheet that you guys have, these formulas are on there, okay, for standard deviation. As says right there. Okay. Notation matters, you guys. Either use them correctly or don't use it at all. You'll definitely lose credit for incorrect notation. The best thing is to just know what you're talking about and know what the notation means. So what's P hat, you guys? It is the sample proportion, so write that down. Okay, what's X bar? The sample mean. So you have a whole bunch of little X bars like we just did, right? Every single person had an X bar for the penny problem. All right, and what's P? Yep, the true proportion or the population proportion. That's the same thing. Okay. What's mu? The true mean or the population mean. What's sigma? Good. This is the standard deviation from the population or the true standard deviation. Okay, and mu of all the little p hats is what? Okay, it's the sampling distribution, but what's the mu mean? So it's the mean of the sampling distribution. So you're taking all the little p hats and you're finding that mean by that graph. So you're looking at the center, right? As long as you have enough of them, that's the true mean. And this one's for proportions since it's p's, right? All right, what's sigma p hat? Yep, standard deviation of the same thing, sampling distribution using proportions. Okay, and now we've got mu x bar. So this is all the little x bars that you would create your dot plot, and you would find that true mean, but this is the mean of the sampling distribution. again. But this time we're talking about X bar, or just a mean, not a proportion. No decimal, no percent, so it's just a number, like year of the penny, okay? Or like your household income, okay? And same thing here, standard deviation of the sampling distribution of X bar. So for all of those with subscripts, you want to think sampling distributions when you're taking a whole bunch of samples. Okay, there's a couple important things to remember. The behavior of X bar in repeated samples is much like that of sample proportions of P hat. Very similar to the last section. So the sample mean X bar is an unbiased estimator of the population mean mu. All right, which is why we're allowed to write that down. Okay, the values of X bar are less spread out for larger samples. So had we done the n equals 25 penny thing, we would have had a less spread out data, right? So their standard deviation decreases at a rate of the square root of n, because that formula is sigma divided by the square root of n. You should use the formula sigma divided by square root of n for the standard deviation of X bar only when the population is at least 10 times as large as the sample. Same rule as before with that 10% condition. These facts are true no matter what shape the population distribution has. We're going to talk about population distributions that are skewed right, skewed left, that kind of thing. All right, Adem. Nope. Okay. This wine stinks. All right, mean and standard deviation of X bar. Sulfur compounds such as dimethyl sulfide are sometimes present in wine. DMS causes off odors in wine, so winemakers want to know the odor threshold, the lowest concentration of DMS that the human nose can detect. Extensive studies have found that the DMS odor threshold of adults follows a distribution where the mean is 25 micrograms per liter and the standard deviation is 7. Suppose we take a simple random sample of 10 adults and determine the mean odor threshold X bar for the individuals in the sample. Okay, so what is the mean of the sampling distribution of X bar? This should take 2 seconds because we're talking about the mean of all the X bars, so it has to match the true mean, right? So just make sure your notation's right, and then it's the same as the true mean. Okay, part B. What is the standard deviation of the sampling distribution of X bar? So this is the formula that you're going to memorize for sampling distributions of means. So that would be this divided by this. But what do we have to check before we're allowed to do this? 10% condition. So we want to know if 10 times the sample, so 10 times 10, is less than or equal to the population. What's the population in this problem? It's like all adults. Okay, so that's true. There are definitely 100 would be less than all the adults. All right, we're good to go. So we can go ahead and find the standard deviation. So we're going to start with sigma. That's the population standard deviation of 7. And we're going to divide it by the square root of 10 because it says we took a sample of size 10. And we get 2.214. Okay, and that's it on that one. So just use the formula and make sure you check the 10% condition. All right, sampling from a normal population. We have described the mean and standard deviation of the sampling distribution of a sample mean, but not its shape. That's because the shape of the distribution depends on the shape of the population. In one important case, there is a simple relationship between the two distributions. So we want to look at some of this stuff. So you guys turn to this page in your book. Anybody got whatever page that is? 493, okay. 453, thanks. And we're going to talk about what these graphs mean. This is a good visual for how we get from one thing to the other. So, Cece, will you read, just start on number 1 for me? Actually, we already did that. We're good. Let's just go to the website, okay? So, on the activity. So, number 2, will you start number 2 for me? Thanks. Yeah.
There are choices for the population distribution: normal, uniform, skewed, and custom. Default, normal, quick, and
Whoa. Oh, you missed it? It's still going. Oh, I have a size of 20. Wow, that's huge. Okay. So we need to know what's happening, okay? What is this graph up here? Yeah, the whole entire population, right? This is everybody. And what's every single one of these little guys? Every sample. So in the penny problem, this would actually be saying I got 2014 and I got 79 and I got, so it's actually not finding the mean yet, okay? And then what's happening here? This is the mean of all 20 of those numbers. You get one mean for all 20 of those numbers, okay? So that's the sampling distributions of mean 20, except we're supposed to start on 5. So I want to do that again. 1, 2, 3, 4, 5. Boom, there's the mean of those 5. Make sense? Okay, so Cece, keep reading for me. All right, we talked about that. We talked about that.
What does the red horizontal band of the population histogram tell us?
All right, what do you guys think? What does this tell us? It matches this red right here. Standard deviation, okay? So that's one standard deviation above and below the mean for the parent graph or the population, okay? So it gives you the standard deviation of 5. All right, what's the next part say, Cece?
Look at the left panel. Important numbers and grid variance. Notice that it causes the numbers match up with the objects to the right.
Wow, you're ahead of the curve.
As you make things happen, the numbers change accordingly, like an automatic force finger.
Ooh, all right, Delaney, read number 3. Go ahead. All right, so we don't have 1,000, so we're going to override to 10,000, okay? So they skip that middle part because that would take a really long time. And they give you the mean of each of those little samples of 5, okay? So now keep reading.
Answer these questions.
Okay. Weird. What kind of shape is this? It is normal, symmetric, right? Okay, keep going. Okay. So the mean up here is 16, and the mean down here is 15.98. Not quite there. All right. What's the next part say? So the population is 5. The standard deviation down here of all the means is 2.2. How'd they get that number? From the formula we just did. 5 divided by, what would this one be? Square root of 5, because we're taking sample sizes of 5. Okay. All right. Are we on the next number? Kyle, what's the next one say? All right, so shapes are pretty similar, right? Both are still symmetric. How about the means? We got a better mean this time of 16, right? It's closer. And how about the standard deviations? Last time we got 2.2. What did we get this time? 1.11. Why is this smaller? Yeah, larger sample size. What are we dividing by in the formula for this one? Square root of 20. Everybody good on this? This is just make sure you understand those graphs. Was there another one? Oh, I don't know. Okay, good. So, as the previous activity demonstrates, if the population is normal, then so is the sampling distribution of X bar, okay? So if it says it's normal, then you automatically know your sampling distribution is normal. So a lot of times they'll tell you that. So if it's normal, you can use mean and standard deviation. So here's an example, and you got to read carefully. Young women's heights, finding probabilities involving the sample mean. So the height of young women follows a normal distribution with mean mu equals 64.5 inches and standard deviation of 2.5. Notice they tell you normal. So if the population's normal, so is the sampling distribution of X bar. So for A, find the probability that a randomly selected young woman is taller than 66.5. Now, here's where you have to be careful. Because of what I just taught you, you guys are going to think that you have to do sigma divided by the square root of n. But on part A, what are we talking about in part A? We're talking about the whole population in part A. It says, find the probability the randomly selected young woman from the population is taller than 66.5 inches. So let X be the height of a randomly selected young woman, would be for part A. You would want to define X, a randomly selected girl height. That's very unorganized right there. There you go. The random variable X follows a normal distribution, right? So we know it's a normal distribution where we have a mean of 64.5 inches and a standard deviation of 2.5 inches. And so we can go ahead and use normal calculations. We're finding the probability where X is greater than 66.5. And so we can do our normal CDF. Do not forget to label stuff. So what's the lower bound in this problem? Good. What's the upper bound in this problem? We could do 10,000 or something, okay? What's the mean? 64.5. What's the standard deviation? 2.5. All right, plug it in, and we get an answer of 0.2119. You would answer the question, and you would say, the probability of choosing a young woman at random whose height exceeds 64.5 inches is 0.21, or there's a 21% chance, okay? So here's where part B is different than part A. Find the probability that the mean height of an SRS of 10 young women exceeds 66.5. This is different because now we're taking a simple random sample of 10. We're not talking about the population. We're talking about those 10 women. So out of those 10 women, what's the probability that we have a greater than whatever it was, okay? So same probability, but now I'm not talking about X. I'm talking about X bar because it's from a sample. So you still have to state, well, it's still normally distributed because now we know if the population is normal, so is the sampling distribution. All right, and then we want our probability. Instead of X on this one, you guys, we have to use X bar. Okay, and the only thing that's going to change when we plug into our calculator is what? The standard deviation. Okay, so I'm going to start with the same thing. All right, and in order to find the standard deviation, we have to use the formula. And before we can use the formula, what do we have to check? 10% condition. So it's 10 people, so 10 times 10 has to be less than or equal to all young women. Is that true? Okay, cool. So it works. Yay, we're good to go. So we plug in our previous standard deviation from the population, which was 2.5, right? Yeah, my screen is so annoying here. 2.5. And we divide by the square root of 10 because our sample size was 10, and we get 0.79. And we plug this in to our normal calculation. And we get 0.0057 for that. Okay, so there's a less than 1% chance, so it's pretty unlikely that out of those 10 women, we would get one whose average, or that we would get a sample where their average height exceeds 66.5. All right, so a lot more unlikely. Changes quite a bit from changing that population. All right, the length of human pregnancies from conception to birth varies according to a distribution that's approximately normal, with a mean of 266 and a standard deviation of 16. Find the probability that a randomly chosen pregnant woman has a pregnancy that lasts for more than 270 days. So for this problem, are we using X or X bar? X. Okay, we're not talking about a sample. We're not taking a sample. So we're just talking about the whole population. So I want to know that they exceed 270. You guys plug this into your normal calculation and tell me what you get. Okay, 40%. You guys get 40? Let's check it. So you got to state, and this is when you guys do these, X is the length of pregnancy. You have to say it follows the normal distribution. Just in case you forgot z-score, you guys, I know I'm not making you show this, but there might be multiple choice questions. So 270 minus 266. So 270 is where we're looking. 266 is the mean divided by 16. That's going to be you got to be able to recognize it at least. All right. But technology, you're going 270 to 1,000. Your mean's 26.6, standard deviation of 16. So there's about a 40% chance of selecting a woman whose pregnancy lasts for more than 270 days. All right, now we're choosing a sample of 6 women, so we're using X bar. Is it still normal? Yes. What changes? Standard deviation. All right, so let's calculate the standard deviation of X bar. We're going to do, what was it, 16? Was that the previous standard deviation, you guys? Okay. Divided by the square root of 6 this time, because we're only choosing 6 women. And we want to know for the sample, what's the likelihood, or I guess just what's the mean? Oh, the first question's super easy. What's the mean, you guys? 266. It's the same as the previous mean, right? And you write it like that. All right. Now compute the standard deviation. Okay, one step at a time. We just did that, so that's easy. We got 16 divided by the square root of 6. Make sure you check the 10% condition. There's 6 times 10 is 60, probably less than all the pregnant women out there. Okay, so you get 6.532 for your new standard deviation. And of course, the last part, we're going to calculate some sort of normal, right? Same thing, out of that group of 6 women, what's the probability that their mean length of pregnancy exceeds 270 days? I'm just going to show you guys the same thing, except for we use that new standard deviation, just like before. So there's a less probability. There's a 27% chance that selecting a sample of 6 women where their pregnancy will exceed 270 days. Okay? I have one worksheet for you.